All right, so this is the last example we're going to look at, and it's going to be the one that's got the most work of the examples we've looked at so far in this section. So in this one, it says that we have a spherical tank and it's full of water, and what we want to do is determine the amount of work that's done pumping all of the water out of this spout at the top. Now, it's a kind of an important observation to make here. An assumption that's being made is when we say that the tank is full of water, we're specifically just talking about the spherical portion of it. Initially, before we start pumping water out, we're not going to assume that there's any water in this little spout here. In order to, if it were, we would have to know more about the size of this spout and stuff to answer this question accurately. So it's really just the spherical tank that's full of water. We're going to start pumping it out of this spout. That requires a force to pump water out of a tank like that. So we could also talk about the work done by that force. Okay, so for this one, what we're going to do is we're going to also set up a Riemann sum like we did for the hanging cable example. And in this case, the way we're going to think about it is we're going to approximate the work done by approximating the force done on layers of water in this tank. And so here's what I mean by layers of water. I'm going to pick little slices, like horizontal slices of this sphere, and I'm going to approximate them by little cylindrical layers like this. Okay? So I want you to imagine, I didn't draw that super well, but I want you to imagine that I picked out like a layer of water and I'm approximating it with a cylinder. And this cylinder is going to have a width of delta x, okay? My goal is to figure out what the volume of this cylinder is. And then if I know the volume, I can determine the mass of water in that cylinder using this. The density of water is known to be 1,000 kilograms per cubic meter. Notice we're working in metric right now. A lot of our previous examples were in imperial. We're dealing with metric units this time. So if I can use the volume of this little cylinder together with the density of water, I can determine its mass. And then from mass, I can come up with the force that's used to overcome gravity pumping this particular layer of water up this spout here. And then I can use the distance that it's traveling up and do, force times distance to compute the work. There's a lot of steps that go into that. So let's kind of take this one step at a time. This diagram is not as helpful as if I take a look at kind of a two-dimensional version of it. So imagine this is kind of a side view here of our sphere, okay? Now what I want to do is, like in the cable problem, I want to impose a coordinate system on this. And there's different ways I could think about how to impose a coordinate system, all of which should give me the correct answer. But I want to choose a coordinate system that makes this as easy on me as possible. So for circles in particular, we're oftentimes going to have the easiest time if we let the center of that circle correspond to the origin. So in my coordinate system, I'm going to think of the center of the circle as 0, okay? Let's get rid of that, come on. All right, and then this is going to be a vertical coordinate system, like this. Can't draw horizontal lines for some reason. Okay, and I want to denote some information here. Now, my picture is not very good, but it's hopefully enough to get you the basic idea of what's going on. So if I'm thinking of this as 0, I'm going to think of the positive direction as up and the negative direction as down, because that's intuitively how we would think of that. What would this be right here? This is the top of this circle. The circle has a radius of 3, so that would be a 3 right there. We know that this guy is 1 meter. So from 3, adding a meter to that would take me up to 4. And then finally, going from 0 down to this bottom part of the circle, I'm subtracting 3 from 0. That would take me to -3. So these are just some relevant points that I'm labeling on my coordinate system here, my coordinate axis. Now, what do I want to do to start working through the problem? Well, again, remember, we wanted to choose individual layers of water that we're going to approximate with cylinders, okay? And then the way that I'm going to choose these layers of water is I'm going to take the entire interval from -3 to 3, because that's where all the water lives, and cut that up into sub-intervals the way that we did for the chain problem. I'm not going to draw them all. Let me just draw one of them. Okay, so I'm going to think of that as one of my subintervals, which we know will have a width of delta x, okay? And then that is going to determine a cylindrical slice that approximates the volume of water in that tank. So let's draw that like this. From the side, that cylinder would look a lot like a rectangle like this, okay? That value right here, where the kind of rectangular approximation is touching the circle, that would correspond to whatever sample point I want to choose from that subinterval. Let's call that xi star, okay? Xi star, that determines this little point right here. All right, now I drew a rectangle, but really I'm mostly interested in just this value right here. So what do we want to do now? Our goal is to compute the volume of this cylinder. This cylinder has a radius, which I'm going to call Ri. But I don't know what it is yet. I have to find a way of figuring that out. Obviously, that radius is going to change depending on where this slice is taken, because this cylinder can be bigger or smaller depending on where it's occurring. So that R should depend on my choice of xi star here, and I want to set up some sort of relationship with that, okay? Now, what I'm going to do is use the center of my circle, and I'm going to construct a little right triangle by drawing a perpendicular line up to this little line right here corresponding to xi star, and then another line going to the circumference of my circle and where it intersects that horizontal line right there. So notice I've created a right triangle. The hypotenuse of that right triangle would be 3. I know this because it's also a radius for that circle, which we know is 3 meters. What is this value right here? This guy right here is the radius of that cylindrical slice, or that cylindrical layer. That's what I've been, there's no star on that one. That's what I've been calling Ri, okay? And what is this height right here? Well, look at how it relates to my coordinate system. It goes from 0 up to xi star. So that is just xi star, okay? I have a right triangle where I know all 3 sides of that right triangle, or at least have labels for them. So I can use the Pythagorean theorem to kind of relate some things here. I know that xi star squared plus Ri squared should equal 3 squared. That's the Pythagorean theorem on this right triangle right here. And remember, because I'm looking for a way of determining the volume of this cylinder, I need to solve for Ri. Or it turns out I actually really just need to solve for Ri squared. I don't even need Ri, because the formula will involve Ri squared. From here, I can see that that would equal 9 minus xi star squared. Just solving this for Ri squared. Pretty easy. All right, now, how do I find the volume of this cylindrical slice? Let's call that Vi, because it's going to correspond to the ith subinterval that we chose here. The volume of a cylinder is pi r squared h. Pi r squared, or in this case, Ri squared, is given in terms of this little formula, this little piece right here. So this becomes 9 minus xi star squared. I actually prefer square brackets. Let's use square brackets. Keep hitting my phone. There we go. Okay, this is the Ri squared, which we solve for right here, times height, which we're showing as delta x. That's the volume of that cylindrical slice in terms of this xi star, this sample point that we chose. Okay? Now, where are we going with this? As we said before, we need to compute the work done, but you can't find the work done lifting or pumping this slice of water out until you know what the force acting on that water is. So because we're working in metric units, we can't find force until we know mass. So we're going all the way back to Newton's second law. I want to find the mass of that slice. I'm going to call that mi. Okay, what is the mass? Well, I know the volume of this slice of water, and I know the density of water in metric units, 1,000 kilograms per meter cubed. Okay, so the mass then is going to be the density times the volume. I need to multiply 1,000 to this. 1,000 pi times 9 minus xi star squared delta x. Okay? Now we need force. Remember, force, Fi, is equal to mass times acceleration, mi times the acceleration. What is the acceleration in this case? Well, kind of like the very first example that we did in this section, we're lifting something vertically. So what we're trying to do is overcome the force due to gravity acting on this cylindrical slice of water. So that means that I need to apply the same force, but in the opposite direction. So I'm still going to call it G, but we know what that is. G is 9.8. So I'm taking my mass, which is here, multiplying it by 9.8. 1,000 times 9.8 is just 9,800. So this comes out to 9,800 pi times 9 minus xi star squared times delta x. We're getting closer, okay? So we have force. Now I need to go from force to work. The work done in lifting or pumping this cylindrical slice of water up to that spout is going to equal the force acting on that slice. So remember, the force is the force that we apply that opposes gravity. We worked it out to be this, times the distance, di, that this has to travel. So now let's work out that distance. Over here in my diagram, if I look where xi star is, remember I'm thinking of xi star as roughly the position of all the points of water within this slice on this coordinate system here. So I'm going to think of the whole slice as moving a total of xi star, or moving from xi star up to this spout here, okay? Now think about what this would be. How far up is this slice going to move? Well, on our coordinate system, I can see that right now it's at a position of xi star, but it needs to move from that up to 4. So the total distance from here to here would have to be 4 minus xi star. That's what that distance is, okay? So this would be equal to 9,800 pi times 9 minus xi star squared. The delta x is going to be there, but I'm going to push that out to the very end. I'm going to multiply by the distance, which is 4 minus xi star. Then I have my delta x, okay? Now I know what comes next. That is the work done approximately on, well, not approximately if I'm thinking of it as an actual cylindrical slice, but that cylindrical slice is an approximation. That's the work done lifting or pumping this cylindrical slice out of that tank. But I have a whole bunch of these slices that I'm thinking about. I just drew one of them here. So I need to sum all of these approximations up for all n of those slices of water, those layers of water, and then add those up to get the total work done. And then we take that sum and we let n go to infinity, which gives me the accurate work done pumping all of the water out of this spherical tank. So I know that the work done is going to be a definite integral because that's what the limit of that Riemann sum is going to turn into. What are my limits of integration? Well, these slices of water, these subintervals that I'm creating, only live between -3 and +3. because that's where the tank is. So that's going to be this, -3 to +3. And then my function is going to come from this. All of my xi stars are just going to turn into x's. My delta x is going to become a dx. And I get 9800 pi times 9 minus x squared times 4 minus x, not squared, just x, dx. And this is what I want to integrate. Let's simplify this down a little bit. I can pull the constant out, 9800 pi. And then I should distribute this out. So if I multiply things out, 9 times 4 is 36. 9 times negative x would be negative 9x. Then I have a negative 4x squared and a plus x cubed dx. Now you can go straight to finding an antiderivative of all of this and working things out, but I want to note something here that helps in problems like this. It's going to help the work to go faster. Notice that the limits of integration are opposites of each other, -3 to +3. We've seen from Calculus 1 that if your integrand is either an even function or an odd function, and if you have limits of integration that are opposites of each other, then there are shortcuts to evaluating these integrals, okay? Now the polynomial in here is neither even nor odd, but I can split it up into two polynomials, a sum of two polynomials where one is even and the other is odd. Specifically, if I were to take the odd powered terms like my negative 9x here and my positive x cubed here and put those into one integral over this way, then together that would be an odd function, an odd polynomial. And then if I take the 36 minus 4x squared, those other two terms, and put them over here and do an integral for just those, that's an even function, okay? So for odd functions, if I integrate an odd function where my limits of integration are opposites of each other, those go to 0. So I can actually just zero out those terms from the very beginning, which is really, really convenient, okay? Then when I'm left with just an even function, what I can do is take the integral only from 0 to 3 instead of -3 to 3, but double the result. Okay, and this is something we talk about in Calculus 1. I'm not going to go through the reason why that is, but if you don't remember, you can even go to my Math 400 videos. I talk about it there. This is going to equal 2 times the integral from 0 to 3 now of just 36 minus 4x squared. Okay, and from here, it's pretty straightforward. Okay, this is going to multiply out to 19,600 pi. That's the 2 times that. And then I'm going to get 36x minus 4/3 x cubed. And we're going to go from 0 to 3. This is arithmetic. I'm leaving that part to you. You can work that out, but it should come out to 1,411,200 pi. And then remember, this is work, but we're in metric units, so we would use joules here. Okay? This was definitely the most lengthy problem that we've done in this section, and it's that, you know, you'll see in the homework there's going to be problems like this. The approach is going to be similar for all of those problems, but with important differences that depend on the shape of your tank. Okay, so the derivation here involved creating these horizontal cylindrical slices. And in other problems, you're also going to be taking horizontal slices. They may not look like cylinders. They might look like rectangular prisms, depending on the shape of this thing. And the way that you come up with these expressions are going to depend on your analysis over here. Okay, so in this case, it made sense to choose a coordinate system where 0 was at the center of the circle. And we used some relationships involving a right triangle in here to come up with the relevant information. Other problems might require slightly different geometry and things like that when you're breaking them down. But the overall idea is still the same. If you need another example, I would encourage you to read through section 6.4 in your book. There is another example like this, but it's not a spherical tank. It's a different shape. that would give you another good example to go on before you start trying these in the homework. That is it for section 6.4.